Welcome back to the course on Foundation Engineering. In today's lecture, we'll be focusing on the different types of shallow foundation, and we'll also subsequently understand little more in detail about your combined footings and Raft Foundation. And we'll also be talking about what is called as your modulus of subgrade reaction and what are the different factors based on which the modulus of subgrade reaction is going to be depending on. So all these topics we'll be covering in today's lecture. So coming to most common types of footings that we are going to come across in the case of shallow foundation. So most of it already we have covered in our introductory lecture of introduction to shallow foundation. But however, we are just trying to have a quick review of what we have seen earlier. So most common types of footings, that's nothing but the shallow foundation, is strip footing, which is basically used in the case if you are going for the construction of a compound wall or so. So where the L by B ratio of that particular footing is what we consider as greater than or equal to 10, that footing is what we call it as strip footing. And next is another is spread footing. Spread footing is nothing but it's an isolated footing whose base of the foundation is spread over certain particular area to carry the load coming from each individual column. So this spread footing, what we are referring here, it can be of square in cross-sectional shape, or it could be a circular cross-sectional one or a rectangular cross-sectional one whose L by B ratio varies in between 1 to 10. Okay. And another type is what is called as ring footing. Ring footing is nothing but it's a hollow circular cross-sectional footing whose depth is extended to a shallow depth, or depth of the foundation is limited from the ground surface. So such footing is what we call it as ring footing. Floating foundation. Floating foundation in the sense, if in the process of construction of your shallow foundation, the soil what we are trying to excavate, I repeat, the soil what we are trying to excavate releases the amount of pressure at the bottom of that pit which you have excavated. Okay, so after the construction of the foundation and the subsequent superstructure there, if the load transferred from that complete superstructure onto the soil, if that load intensity is less than that of the load intensity of what you have excavated, then such kind of foundation what is constructed to transfer the load coming from the structure onto the ground or the structure onto the soil strata at the footing level. So that foundation is what is called as floating foundation. Combined footing. So in case if the load coming from individual columns, in one case of load carried by the column is heavy and the load carried by the other adjacent column is less. So in order to have a uniform load distribution happening across, so we go for what is called as your combined footings. So most common type of combined footings what we come across are your rectangular footings, which we have already talked about in the introductory lecture, and the other type is your trapezoidal footing. Okay, so in which case we go for rectangular shaped combined footing, in which case we go for trapezoidal shaped combined footing, already we have learned, and we'll also just have a quick look at in the next coming slides. And the other type of footing is strap footing, which is also one type of combined footing only, where you have two individual footings which are connected by means of what is called as a strap beam. Okay, let's say this is one footing. I have another footing at the same elevation from the ground. If this is my ground, at the same depth, both the footings are existing. Depth of the foundation in both the cases is same. But however, the load coming from, let's say this is P1 load from column 1 or from footing 1, and this is P2 load. If P1 load is greater than your P2 load, so in order to have a uniform pressure getting distributed from both the footings onto the soil strata, because as P1 load is more, obvious that the pressure what gets transferred from that footing which is taking that P1 load onto the soil, that pressure distribution is going to be high when compared to that of your second footing which is carrying the load P2. So in order to have a uniform pressure distribution to exist, so what we can do is these two footings are going to be connected by means of what is called as a beam, and this beam is what is called as a strap beam. So what does this beam does? If footing which is carrying the load P1, if it is trying to transfer heavier pressure onto the soil strata, so it redistributes the load from one footing onto the other footing and vice versa. So whichever footing is trying to distribute more pressure, so from that footing, beam transfers the load onto the other footing, and a redistribution of the load takes place with the help of the beam which is connecting those two individual footings. So such kind of footing, such kind of combined effect of your footings is what we call it as your strap footing. This is also one type of your combined footing only. And other type is cantilever footing. So the functionality of this cantilever footing is as similar to that of your strap footing, but however, in the case of cantilever footing, when two individual footings are at different elevation, and if you want to redistribute the load from one heavier load coming from one footing onto the load which is to be distributed onto the other footing, then those two footings which are existing at two different depths below the ground surface, okay, so those two footings are going to be connected by what is called as a beam which is of cantilever shaped cross section. So that is what we call it as a cantilever footing, which is also one type of combined footing only, which is trying to, there the cantilever member what is trying to connect those two individual footings at different elevation is trying to redistribute the load from one footing onto the other footing in order to ensure a uniform pressure distribution happens from that footing onto the soil which is there below it. And next is a raft or a mat foundation. Okay, raft or what is meant by a mat foundation. What is meant by a mat? Mat is nothing but it is what is a foundation which is spread over relatively a large area to take the load which is coming from two or more number of columns. This is such kind of foundation is what we call it as your mat foundation. Or the soil which is there below the foundation what you wanted to construct, if it is a weak soil, or in case in that particular construction site for the total number of columns which are trying to carry the load coming from the superstructure, if isolated footings are to be constructed to carry the load coming from all individual columns, if those isolated footings in the construction of them, if it is covering the area of that complete construction region, if the area what is required for the construction of your isolated footings to carry the load coming from individual columns, if the area covered by the isolated footings construction is greater than 50 to 60% of the plan area of your construction, then in such particular case, we go for the construction of a single monolithic structure. Okay, single monolithic structure, which is what we call it as raft foundation or mat foundation. Mat is nothing but it's a spread of an individual foundation over the complete plan area of that construction to carry the load coming from group of columns which are trying to carry the loads of your superstructure. So from the superstructure, those individual columns carry the load and redistributes the load over the complete area of that raft region. And from that complete area of the raft region, because of the rigid action of that raft region, the load is assumed to get distributed onto the soil below the raft, which is more or less uniform in nature. Okay, so that is what is the functionality of your raft or mat foundation. Coming to the different types of rafts, we are going to see various different types of rafts apart from what we have listed here. These are some of those types of rafts what you would be in general coming across with. One of such type is raft with uniform thickness. So when you are trying to talk about that mat or a raft which is spread over the complete area, plan area of your construction. So if the thickness of the complete raft foundation is same throughout, then such kind of raft foundation is what is called as raft with uniform thickness. Another type of raft foundation like raft with beams, where columns are resting on beams and beams on raft. So what generally happens in the case of your raft with uniform thickness is columns would transfer the load directly onto your raft foundation. But here in this second case, load comes from the columns, gets distributed onto your series of beams on which the columns are constructed, and from those beams your load gets redistributed onto your raft foundation. Okay, so such kind of raft is what we call it as raft with beams, where columns are resting on beams and beams which are resting on your raft. And this is another type of your raft foundation. Here in this case, earlier case, load was coming from the column, getting distributed onto your beams, and from the beams, load was getting redistributed onto the raft, and from the raft, the load was distributed onto the soil, which is there below the raft. But here in this case, raft is taking the load from the columns, and the load which is carried by the raft is redistributed onto the set of beams which are there below the raft, and from those beam cross sections, the load gets redistributed onto the soil on which that particular beams are going to be resting on. So this particular type of raft with inverted beams is something what you can prefer in the case of your expansive soils, so that now you have some free space what is available below the raft region in between your beam cross sections which are there below the raft. So in between that individual beams, okay, you have some free space, so that whatever the free expansion which was supposed to be happening in your expansive soil, that free expansion can be accommodated into that free space what is available, so which can result in minimizing what is called as the effect of swelling on such kind of foundation. And likewise, you'll also have different other types of rafts in your literature or in any of the standard textbook. Depending on your requirement in the construction, people go on to use different types of your raft foundation. So they might have some pedestals constructed. Let's say, for example, load comes from the column, gets distributed onto a pedestal, and from that pedestal, load gets redistributed onto the raft region. So that is one type of raft which you can also generally come across. And in some cases, column would directly transfer the load onto your raft, and from the raft, in the form of a pedestal which is spread over certain width, your load gets redistributed onto the soil which is there below that particular raft region. So you'll have various other different types of rafts which are generally used in the construction of your superstructure. So now, after understanding what are the different types of shallow foundations that we come across with, now major important aspect what we need to know is at what minimum depth I should be constructing that particular shallow foundation. Can I construct your shallow foundation at the ground? Ideally, no. Okay, so we cannot construct your shallow foundation directly on the ground surface for various reasons what are mentioned here. So what we say is that according to the Indian Standard Code 1904 of 1986, so minimum depth at which the foundation has to be constructed, the shallow foundation what we are referring to. So the minimum depth at which it has to be constructed is something around 0.5 meters to 1 meter. In some cases, people do consider it as roughly around 0.9 to 1 meter. So, but however, the minimum depth at which the foundation has to be, shallow foundation has to be constructed is 0.5 meters. Why we need to provide that minimum depth of 0.5 meters is to minimize the effect of covering of the soil because of the runoff water, or to minimize the effect of various other aspects because of your erosion or various other things. Okay, so your foundation, what we are referring to, shall be placed. Okay, it's not that minimum depth of 0.5 meters, if I satisfy, I can go on to construct my foundation. It's not that. Okay, so you should also take care of the various other aspects, whether I have got any problematic soil existing in that particular zone where I am constructing my foundation and so on. So, and whether you have got any fluctuation of water table which is affecting your foundation what you are constructing. So all those particular aspects are also to be taken care of. So foundation shall be placed below the zone of excessive volume change due to moisture variation. So in the last lecture we said over the first 2 to 3 meters of depth, if you have what is called as your expansive soil, so generally the moisture content variation you will be typically seeing over a depth of 2 to 3 meters or 3.5 meters depth below the ground surface. Only within that depth of the region you will see the variation of moisture content which would result in the variation of the volume of the soil. So it is better you avoid the construction of the foundation in that particular region of that expansive soil where you have the variation in the moisture content. So below that particular depth of 2 to 3 meters, if you go on to construction of your shallow foundation, though below that 2 to 3 meters, still if you have got your expansive soil, still, you are not going to find much effect on your shallow foundation what you are going to be constructing, because beyond that 3 meters or 3.5 meters you are not seeing much variation in the moisture content value of that soil. So if there is not much variation in the moisture content value of the soil, so your expansive nature in the soil below the foundation will not affect your foundation at all, because there will not be much variation in the volume of the soil there. And we should be looking at the condition that if your soil which is there at the nearer to the ground surface, if it is an organic soil or soil which gets decomposed with the time, so you should not be constructing the foundation in that particular depth of the soil strata, or you should be avoiding the construction of the shallow foundation in the region of the soil strata where consolidation settlements have not completed because of any reason. Let's say if your region where you wanted to take up the construction was a low-lying area where the soil got deposited in that low-lying region, or municipal solid waste deposits were filling that region where that municipal solid waste deposits consolidation, the process of consolidation in that soil deposit is not completed, or the complete decomposition of the material didn't happen by the time you went on to construct the foundation there. So in all such particular case, the depth at which the foundation has to be constructed is below that municipal solid waste deposited region. Below that depth only you should construct your shallow foundation, or below the depth of your organic material, or below the depth of the top soil layer which got found because of wind effect or various other reasons. So you should avoid that depth of the soil strata, and below that depth only you should be constructing your foundation. And foundations adjacent to your flowing area where you have what is called as any river bodies flowing or any water stagnated regions existing. So adjacent to that particular area immediately, you should avoid the construction of your foundation in order to ensure that your scouring effect or erosion effect do not happen on your foundation. Because if you construct the foundation adjacent to your river bank or so, there is a possibility whenever you have floods or whenever you have a heavy flow of water, erosion of soil can happen below the foundation, which could result in what is called as a failure of the foundation there. And in a case where you have water table fluctuation, okay, in the region of the soil strata where you have the effect of water table fluctuation, which could certainly cause the damage to your foundation because of by causing what is called as a floating condition in your structure, or whenever there is a rise in water table, then effective stresses getting developed in the soil below the foundation decreases, which would result in lesser load carrying capacity of that particular foundation, because the soil below the foundation will have lesser effective strength, okay, where the load carried by that particular foundation gets decreased, resulting in the failure of the structure in some particular case. And you should avoid what is called as waterlogging effect happening around the foundation what is getting constructed. It means that water should not get stagnated around the construction region of your foundation. So if your water gets stagnated around the site or around the surroundings of the foundation, then there are all possibilities that the foundation what is constructed might get damaged, or the strength of that foundation can decrease over time because of the erosion effect in the steel bars which are placed inside the construction of that particular foundation and so on. So you should have a proper drainage system available around your foundation what is constructed, so that any stagnated water around the foundation can properly get drained off, which would not cause effect on your foundation what is constructed there. And whenever you are taking up the construction of footings on rock surface or sloping rock surfaces, you have to be little careful, because your foundation shall not be directly constructed on the surface of your rock. Rather, the top surface of the rock has to be little chipped, so that whenever you are taking up the construction of your foundation on that particular chipped surface, a proper bond gets developed between your foundation and your rock strata which is existing there. And in case if you are constructing your foundation on sloping surface of your rock bed, so you should structurally, in the structural aspect, you should try to provide what is called as dowel bars to have a proper stable connectivity between your rock and your rock bed and the footing, so that the instability of your foundation do not come into picture because of that sloping rock bed what you are encountering. And whenever you are coming across with the footings adjacent to the existing structure, let's say already in the surroundings of your construction site, the buildings are existing. Now, within your area, you are taking up the construction of your structure. But in the process of construction of your structure, you should understand what is going to be the effect of the adjacent structures on your construction and vice versa. Vice versa in the sense, your construction, how is it going to be affecting the adjacent structures? Let's say, for example, I have already my adjacent structure, and in this construction region, I am trying to excavate the soil. In the process of excavating the soil for constructing the foundation for my structure, so what is going to happen is the soil which is there below the foundations of the existing structure would try to heave towards your region what you have excavated, okay, which could result in the failure of the existing foundations of those structures. So you have to be little careful when you are taking up the construction of your foundations adjacent when already the structures are existing adjacent to your construction site. Okay, you have to take care of the load transfer, how it happens from your foundations, and what is the region within which your load transfer is happening from the footings which are existing in the case of your adjacent structure. So in case if the load transfer region of your footing and the adjacent footing is getting overlapped, if you see the pressure bulb of your footing and the adjacent footing is getting overlapped, so within that overlap region, there are all possibilities that the strength of that overlap region of the soil strata could decrease, resulting in the failure of your foundation or the failure of the other adjacent foundation. So you have to minimize the effect of what is called as your overlapping effect or interference effect of one footing on the other footing to minimize the effect of excess settlements that are going to be happening in those foundations. So understanding little more in detail of about your geotechnical aspects of the combined footing. So geotechnical aspects here in the sense, so how do we fix up what are the dimensions of that particular combined footing depending on the load which is expected to be coming from your columns. Okay, so how the dimensions of those combined footings are to be fixed, how we have to design your combined footings, whether it could be a rectangular combined footing or a trapezoidal one or a strap footing or cantilever, but our main focus would be with respect to your rectangular combined footing and trapezoidal combined footing. So what shall be the width of that combined footing, what should be the length of the combined footing in the case of your rectangular one, and in the case of a trapezoidal one, okay, what shall be the smaller width, what shall be the larger width of that trapezoidal cross section, and what shall be the length of that trapezoidal combined footing. So all that we should be understanding depending on load intensity, what was supposed to be carried by that particular combined footing. In which particular case we go for rectangular combined footing, in which particular case we go for what is called as your trapezoidal combined footing. So all that we need to be understanding. First, let us know when is that we prefer to go for what is called as your combined footing. Okay, so combined footings are preferred when the columns are spaced too closely, that if isolated footing is provided, the soil beneath that particular isolated footing may have a part of what is called as common influence zone. So when the isolated footings are to be constructed to carry the loads coming from those two closely spaced columns, so when one footing and the other adjacent footing is trying to carry the load coming from those two individual isolated footings, isolated columns, so if the load distribution happening from one footing is getting interfered because of the load distribution happening from the other footing, whenever you have the interference of those two isolated footings which are to be constructed nearby, so in order to avoid that interference effect of those two near adjacent footings, so you can go for what is called as a simple combined footing to carry the loads coming from those two individual columns. Or whenever the bearing capacity of the soil in such isolated footings what you are planning to design will require an extent of column foundation to go beyond the property line. So let's say if your boundary region of the construction is limited, but however to carry the load or to minimize the pressure coming from the footing onto the soil because of the load what is coming from the column, so load is heavy. So for minimizing the pressure, what I should do is I require a large area to carry that heavy load. So in the process of providing a large area to minimize the pressure, because pressure can be minimized by providing a larger area to distribute that particular load coming from the column. So in the process of minimizing the pressure from the footing onto the soil below that, because the bearing capacity of the soil below that particular foundation is less. So in such case, if the bearing capacity of the soil there is less, then the pressure what is to be distributed from the foundation onto the soil should also be less. So in order to minimize the pressure, what I can do, if the load expected from the column is heavy, then I require a large area to distribute that load. But in the process of providing a large area, if the dimensions of that particular footing what I wanted to provide, if it is going beyond your property line, beyond your boundary of the construction, then in such particular case, I cannot go on to construct the foundation in some other's construction or some other's property. So I have to construct whatever I want within my boundary of the property region only. So in such particular case, if the constructed or if the footing what you are planning to construct, if it is going beyond your property line, in such particular case, you should construct what you should go on to construct what is called as your combined footing. So where you cannot extend the width of the footing or length of the footing beyond your property region. So in the other direction, wherever the space is available, you can go on to extend your footing so that the pressure distribution from the footing onto the soil can be minimized so that your failure in the foundation will not happen. So most common types of combined footings which we are going to be coming across is with rectangular shaped combined footing and trapezoidal shaped combined footing. So in the case of rectangular shaped combined footing, so how do we understand what shall be the length and width of that particular combined footing that I am supposed to be providing? So in which particular case I should be going for your rectangular shaped combined footing. If two or more columns are carrying almost equal load, I don't say exactly two columns are going to be carrying the same load, but more or less nearer in one case, if the load carried by one column is, let's say, 100 kilonewton, in other case, if it is something around 110 or 120 or something, is the load what is to be carried by the other column. So in such particular case, if two or more columns are carrying the load which is more or less nearer to each other, in such particular case, you can go for what is called as your rectangular combined footing. So in the process of constructing that rectangular combined footing, I'll be requiring what shall be the length of that combined footing and what shall be the width of that rectangular shaped combined footing. So in the process of proportioning the dimensions of that particular foundation, proportioning in the sense, in order to know what shall be the width and length of that particular rectangular shaped footing, rectangular shaped combined footing. So let us go on to understand what shall be the steps that I should follow in ultimately knowing what is the length and width of that particular rectangular combined footing. So first we'll try to find out what shall be the area that we require for that rectangular combined footing. Okay, so how do we know what is the area that I should construct there to safely transfer the load coming from your two or more number of columns? So to safely distribute the load from those columns through the foundation onto the soil below that, how much area of the foundation is required? So first step is that. So how do we know how much area is going to be required? So the area what is required is nothing but, generally, if you can recall, pressure or stress is nothing but load by area. Now what I am trying to talk about is area. So area is nothing but load by Q. Here Q, what I am referring to is nothing but the net allowable pressure. Okay, so how much net allowable pressure you wanted to transfer through your foundation onto the soil? So that net allowable pressure is what you should be knowing, and Q1 plus Q2. What is this Q1 plus Q2 referring to? So Q1 is, let's say, the load coming from the column 1, and Q2 is the load coming from your column 2. So Q1 plus Q2 is nothing but the resultant force what is expected to be transferred, through your footing onto the soil, the total resultant force from column 1 and column 2. That's nothing but Q1 plus Q2. So total load is Q1 plus Q2 is what you wanted to transfer through that rectangular combined footing, and the net allowable pressure or net allowable capacity of that particular soil is QA net or Q net allowable. Is other way I can write it. So once from that I know what is the area of the foundation. Okay, sir, how do I know what is your Q net allowable? Okay, without knowing the width and length, I cannot go on to calculate what is your ultimate bearing capacity of the footing. If I don't know ultimate bearing capacity of the footing, I cannot say what is your allowable bearing capacity. And if I do not know allowable bearing capacity, then I cannot say what is your net allowable bearing capacity. So first what I can do is I'll assume some Q net allowable. Roughly assume something. For that assumed value, with Q1 load coming from column 1, Q2 load coming from column 2, if it is known, then calculate the area of that footing. And once the area of the footing is known, for that assumed value of net allowable bearing pressure or bearing capacity, then go on to calculate where does the location of the resultant of these two forces going to be passing through that particular footing what you are trying to design there. Okay, so the position of that resultant force, let's say I know what is Q1 load position, Q2 load position. So let's say I am trying to take, I am applying an equilibrium condition, net summation of moments about the column 1 position if I equate it to 0. So what I'll see is Q2 into the center to center spacing between those two columns is S. So Q2 into S has to be equal to Q1 plus Q2 into X bar. So that's nothing but X or X bar is what we are calling it as the centroidal distance. At what centroidal distance from the center of your column 1, the resultant force is going to be passing through. Okay, so that position of your resultant force X is what I can write it as Q2 into X by Q1 plus Q2. So which I am going to be getting it like this. So which is nothing but Q2 into X, which is in the clockwise direction when I am applying your moment equilibrium condition about the center position of your column 1. So Q2 into X, Q2 into S in clockwise direction. So which is minus, and resultant force has to balance your net effect of that. So this Q2 into S should be equal to Q1 plus Q2 into X. So from this we say X should be equal to Q2 into S divided by Q1 plus Q2. Okay, so the resultant force at what position it is going to be there from the center of that column 1 is what I know now. So X is that resultant force location. So for uniform pressure, in order to ensure that a uniform pressure distribution happens from your footing onto the soil, okay, so for uniform pressure distribution under the foundation, the resultant load should pass through the center of your foundation base. So in such particular scenario, the length of that particular foundation, the length of that combined footing what I am going to be providing is nothing but it is equal to L1 plus 2x. What does this L1 means? So from the center of your column 1 to the edge of that combined footing, let's say some minimum space is what I should provide. So that distance is what we are calling it as your L1 distance. Approximately around 0.5 meters is the minimum distance what we try to provide from the center of your heavily loaded column 1 towards the edge of that particular footing. So that is a minimum distance of, let's say, 0.5 meters. And the centroidal distance or the location of that particular resultant force where it is going to be passing through from the position of your center of the column 1, it's nothing but we call it as X distance. And this remaining distance to the other edge of that particular footing is also approximately what we get it as other X distance. Okay, so from that we say the length of that particular foundation shall be equal to L1 plus X plus X. So total put together is nothing but L1 plus 2x. So once I know what is total length of the footing, then the other L2 distance, what I should minimally have from the center of your column 2 to the other edge of that particular combined footing is nothing but total length is L minus the center to center spacing between those two columns. Yes, onto one edge it is the L1 distance. So automatically L2 is nothing but L minus S minus L1, where that L2 value what we are calculating should be greater than or equal to 0. That is something what you should check it for. And once the length of the combined footing what you are trying to look at is known, then you can go on to calculate what is the width of that combined footing, because the area of that combined footing what was required is already calculated. So as the length is known, area is known, then I can go on to calculate what shall be the width of that particular combined footing. So once I know what is the width, then I'll go back to your bearing capacity equation according to either Terzagi's theory or any of those theories. So from that particular bearing capacity expression with this particular width, I'll go on to calculate your ultimate bearing capacity. From that, allowable bearing capacity. From that, net allowable bearing capacity. So once I get that net allowable bearing capacity, then I'll come back to the first expression what we have seen, where we have calculated your area of the foundation. So I'll come back to this equation again. I'll substitute the new value of your net allowable bearing capacity. With this new value of your net allowable bearing capacity, I'll calculate the area of the combined footing required once again. Length of the combined footing is what you have already calculated. Now calculate the new value for the width of the combined footing. So for this new value, then once again go on to calculate your Q net allowable. From that, get the area of the footing. From that area of the foundation, get what shall be the required width of your foundation again. So you continue to iterate it until that in the next successive steps of iteration, the width of the combined footing what you have got is not much changing. Then stop your iteration process, and that becomes what exactly should be the width of that combined footing. And length of the combined footing is anyhow known. So once the length and width of the combined footing is known in terms of the geotechnical aspect, so you understood what shall be the cross-sectional dimensions of that particular rectangular combined footing in order to ensure that a uniform pressure distribution happens from the combined footing onto the soil. So in order to redistribute the load coming from the individual columns, in order to ensure a uniform pressure distribution happening from that footing onto the soil, so I require so and so width and so length for that particular combined footing. That's how we go on to calculate it. In similar way, for trapezoidal footing also we do similar kind of procedure for calculating what shall be the dimensions of that particular trapezoidal combined footing. Here the dimensions of the trapezoidal combined footing, when we are talking about, it's the length of the combined footing, the smaller width of that trapezoidal footing, and larger width of that trapezoidal footing. So all that we have to clearly understand. So when do we go for this trapezoidal combined footing? If one of the columns which is carrying load which is relatively higher when compared to that of the load carried by the other column, so in such particular case, we go for what is called as your trapezoidal combined footing, because the load which is trying to carry more load requires more area for a uniform pressure distribution or uniform load transfer. So in the process, it is not economically acceptable to construct the complete foundation with the larger cross-sectional dimensions. So what we need to understand is, wherever the load coming from the column is more, there you require larger area for a uniform pressure or uniform load transfer. With the load coming from a column, if it is less, it requires a lesser area only for load which is to be distributed onto the soil, which is more or less uniform in nature. So wherever load is more, area required is more. Wherever the load transferred is less, the area required to distribute that load onto the soil is also less. So in such particular case, we prefer to go for what is called as a trapezoidal footing. Instead of going for a rectangular combined footing, we prefer to go for what is called as your trapezoidal combined footing. So here in this particular case, we are saying, let's say for example, if your Q2 load is greater than your Q1 load, so in such particular case, the area required to distribute the load coming from your column 2, the area required is also more. That's the reason why you are providing a larger width in the region nearer to that column 2 when compared to that of the width provided in the region of your column 1. So that if width is more, the area available for distributing that load is more. If width is less, the area available for transferring that lesser intensity of load, so the area required is also less. Okay. So for calculating what shall be the dimensions of that trapezoidal footing, certain terms is what we should in prior know before we take up the calculation of the other unknown parameters or other unknown values. So proportionating of your foundation will involve the following steps. But however, before we talk about proportionating, in the sense knowing about the dimensions of your foundation, certain values are first to be assumed. Assumed in the sense you have to fix them. I don't say assume, you have to fix those values. You should know those values before you go for the calculation of the other unknown values. That is, the length of that trapezoidal footing is something what you have to fix initially itself. And the L1 value, what you are going to be providing, is something approximately a constant value. It depends on the size of the column also. Okay. So we should look at the size of the column 1 and the freeboard space of something 0.5. So that by ensuring that freeboard space and half distance of your column 1. So by knowing that, you will be able to fix up what is your L1 value. So roughly you have to fix up what shall be the length of that particular trapezoidal footing, knowing where is the position of column 1, column 2, and accordingly the freeboard spaces that you are required to be providing on either side of the columns which you are trying to have in the construction of the combined footing. So based on that, so you have to fix up what shall be the length of that trapezoidal footing. Okay, so length is known, length of that trapezoidal footing is known to you. Now the area of the combined footing in the similar way how we have calculated earlier, we will be doing it. The location of the resultant force, how we have done it in the earlier case, is what we are going to be doing it. And for uniform distribution of the pressure under the foundation, the resultant load should pass through the center of your foundation base. And this is the expression what we will be making use of to understand the position of where the centroid of or center position of that foundation base is going to be existing. The centroid position of that foundation base is going to be existing. Okay, so here small x refers to that of at what centroidal distance the resultant force of that load that is to be distributed through the combined footing is going to be existing from the position of column 1. L1 indicates that from center of column 1 to the free end of that column 1, towards the free end of the position of the column 1, what is that distance? B1 indicates the width of that combined footing, smaller width of the combined footing. B2 here indicates the larger width of the combined footing. L indicates the length of that particular combined footing. Okay, so this is one equation, and the other equation is the area of the combined footing. So here the area of this particular combined footing means that it's a trapezoidal footing. So in the case of the trapezoidal footing, the area is calculated as B1 plus B2 by 2 into the length gives you what is the area of the combined footing. So if I look at these two equations, this equation and this equation, I have got only two unknowns, that is nothing but B1 and B2, because x is what I can calculate from the above expression. L1 is what you already initially chosen that value. Length of the combined footing is what you have initially chosen. Okay, so only two unknowns are your B1 and B2. From these two equations, calculate those B1 and B2 values. Once the B1 and B2 values are known, then go back to your fundamental expressions of bearing capacity to determine the ultimate bearing capacity of that combined footing. So once the ultimate bearing capacity is known, then calculate allowable bearing capacity, then calculate net allowable bearing capacity. From that net allowable bearing capacity, once again come back to this expression of area of the foundation what is required. Okay, so once you know area of the foundation what is required, then substitute that value in this equation. Okay, so and once again solve for these two set of equations whatever you have to get new values of B1 and B2. Once you get the new values of B1 and B2, make use of that to calculate once again the net allowable bearing capacity and iterate this process ultimately to get what shall be the values of B1 and B2. That's the width of that trapezoidal combined footings. So you have to calculate it. So once the width is known, B1 and B2, the length is already a fixed value what you have fixed based on the position of the columns. Okay, for constructing the combined footing. So length and width is known of that combined footing. So that's how geometry of that combined footing is going to be proportionated in the case of your trapezoidal combined footing case. Next is in the case of your raft or mat foundation. So what is meant by a raft or a mat foundation means raft is nothing but it's a type of a foundation which is basically used when the base soil or the soil below that particular foundation what you want to construct has got a lower bearing capacity. If the soil is a weak soil or the bearing capacity of the soil is less below the region where you wanted to construct the foundation. So in such particular case, it is not advisable to go for the construction of your isolated footings or combined footing of rectangular or trapezoidal shape. So what we prefer to go for is a foundation which is spread over a large area, so that though the bearing capacity of the soil is less, I can ensure to see that the load distribution happening from that footing onto the soil will meet the criteria of that bearing capacity of the soil. The pressure what you are trying to transfer through that particular foundation onto the soil is going to be less than that of the bearing capacity of that particular soil to ensure the safety of the structure there. Okay, so in all such particular case of the soil where you have lower bearing capacity existing, or if the column loads are so large that the area required for the construction of your isolated footings for carrying those column loads is covering the plan area, which is more than that of your 50 to 60% of the plan area of the construction. So in such particular case also, we prefer to go for what is called as your raft foundation. So what is going to happen here, as raft is nothing but it is called as a monolithic structure which is constructed over the complete plan area of your construction. So area of the foundation what you are constructing is large now. The load what is coming from all individual columns has to be uniformly distributed through that particular large carpet area of the foundation what you have provided. So load by a large area is going to give you a lesser pressure distribution happening from that foundation onto the soil. So if though the bearing capacity of the soil there is less, so as the pressure what you are trying to transfer through that particular raft onto the soil is less, so it can meet the criteria of your bearing capacity of that particular soil without causing any failure in your foundation by preferring to go for what is called as a raft foundation. Okay, in the case of your raft foundation, through that raft when the loads are getting transferred because of individual columns which are connected to that particular raft foundation. If you look at here, this is one column, this is another column. You have multiple columns which are trying to distribute the load onto this monolithic structure which are calling it as your raft foundation. So let's say here I have marked some 12 columns. These 12 columns are carrying some load. It is trying to distribute some load from them onto the raft foundation, and through the raft a uniform pressure distribution is what you are assumed to have, or a uniform pressure distribution is what you wanted to have through the raft onto the soil. But however, you will not exactly have a uniform pressure distribution happening through the raft onto the soil, but you can go on to understand depending on the position of the raft. Through, if this is what I consider it as my raft foundation, at this point how much is the stress that you are trying to transfer through the foundation onto the soil? At this point, how much stress you are trying to induce from the foundation onto the soil? At this point, how much stress you are trying to induce? At another point, how much stress you want to, how much stress you are trying to induce because of the loads which are coming from different columns which are proportionate in that construction. Okay, so if I want to calculate that stress, I can try to calculate it as from this particular expression what is given. So here, this is not something new what I am showing you here. So if you can recall from your mechanics of materials or strength of materials course, where you have talked about what is called as the combined stress, okay, which you have calculated in the case of your beams. Okay, so combined stress because of the direct load, because of your bending effect and so on. So the stresses what you have calculated. So from the same expression we are trying to talk about here, which is nothing but R by A, where R is nothing but it is the resultant force of the loads coming from all those columns which are connected to your raft. So resultant force R here is nothing but it is equal to load coming from column 1 plus column 2 plus column 3 so on. If you have n number of columns which are structurally connected to the raft, so resultant of all those forces, all those loads which are coming from those n number of columns which are connected to the raft. So resultant force is R. A, capital A here indicates it's the area of the raft. Area of the raft, how do we calculate? It's nothing but the width of the raft into length of the raft. Plus or minus mx. Mx here indicates your moment, how much moment is getting developed about your symmetric x-axis of that particular raft foundation because of an eccentric load. Let's say the resultant of all these forces will not be exactly passing through the centroid of the cross section of your raft. It might have some eccentricity. This is a position, let's say for example, this is a point through which the resultant force is to be passing. But whereas the centroid of your raft structure, this is the centroid of the raft. This is the position of your resultant force. So what is happening when the position of the resultant force is not passing through the centroid of that raft foundation? Then it means that the loading, the resultant force is eccentric with respect to the centroid position of that particular raft. So whenever you have got some eccentricity involved now, so because of that eccentricity, there will be a moment of couple which also gets generated about your symmetric x-axis and symmetric y-axis due to that eccentricity what you are coming across with. So mx moment about x-axis, my, moment about y-axis, is because of the eccentricity what you have got with respect to the position of your resultant force, what is to be distributed through that raft foundation onto the soil. Okay, so that's what we can calculate. Mx is nothing but resultant force into the corresponding eccentricity what you have got for generating the moment about x-axis. So moment about x-axis in the sense it is the distance in the y direction. The perpendicular distance what you are going to be talking about is the distance in the y direction. So that distance in the y direction is what we call it as Ey, eccentricity in the y direction. So while calculating moment about x-axis, it's resultant force into Ey. While calculating moment about y-axis, it's nothing but resultant force into eccentricity in the x direction. Because in the x direction, whatever distance that is existing, that I'll call it as a perpendicular distance when I'm calculating the moment about your y-axis. Okay, so that's how you get what is moment about x-axis and moment about y-axis depending on the eccentricity of that resultant force. Depending on the position of that resultant force, where is it acting with respect to the center of the centroid of that raft foundation. So you will be knowing what is the eccentricity in the x direction for that resultant load and eccentricity in the y direction. And in this expression, Ix and Iy indicates it is moment of inertia about x-axis for that cross section of the raft foundation and moment of inertia of that particular raft foundation about y-axis. So moment of inertia about x-axis is what I'll write it as BL cube by 12, and moment of inertia about y-axis is nothing but LB cube by 12. So Ix is known, Iy is known, Mx is known, My is known, resultant force is known, area of that raft foundation what you are trying to provide, which is nothing but it is the plan area of the construction. Okay, that is known. Then at whichever position you wanted to calculate the stress that is getting transferred from the foundation onto the soil, you can go on to do that. So if I want to calculate how much is the stress that is getting transferred through this particular portion of the raft onto the soil, how much stress is getting induced or how much stress is getting developed. So I'll try to understand where is that point from the centroid of the raft, at what distance that point is there in x direction, in y direction, and accordingly I'll be substituting into the expression to get how much is the stress that you are trying to induce from the footing onto the soil below it, below that particular raft. That's how you go on to calculate the pressure what you are trying to transfer or distribute from the raft onto the soil because of the resultant force what you have calculated, which is to be distributed through your raft foundation onto the soil. And next aspect and the last aspect which we have already touched upon, but we'll try to understand little more in detail, is nothing but it is your modulus of subgrade reaction. So what is this modulus of subgrade reaction mean? So modulus of subgrade reaction is nothing but it's the reaction pressure which is sustained by the soil. Okay, so it's nothing but the pressure what is sustained by the soil under a rigid plate of standard diameter per unit settlement measured at a specified pressure or settlement. So that reaction pressure what is sustained by your plate when it is undergoing certain amount of settlement, or in the simple terms, this modulus of subgrade reaction can be defined as the ratio of pressure causing a uniform or unit settlement in that particular plate what you are looking at, or in the foundation what you are looking at, which is resting on some soil. Okay, so that ratio is what we call it as your modulus of subgrade reaction. So where the modulus of subgrade reaction is denoted by the notation small k most of the times. Okay, so which is given as pressure P by settlements indicated as delta. So we try to transfer some amount of pressure through that particular plate onto the soil, and we go on to measure how much settlement is happening in that particular plate due to that induced pressure through the plate onto the soil. So pressure causing the corresponding settlement in that plate. So that ratio is what we calculate, and that is what we call it as your modulus of subgrade reaction. So how do we get this modulus of subgrade reaction? Means we are going to be calculating this modulus of subgrade reaction value from your plate load test. So in the case of plate load test, what we do, we consider a rigid plate of minimum thickness of 25 mm, of which is having some standard dimensions. If it is a square plate, let's say 30 centimeters by 30 centimeters. If it is a circular plate of standard dimensions, some 30 centimeters or 45 centimeters, whatever it is. So of some standard dimension rigid plate is what I am going to be using in the test, and due to the load what you are trying to transfer through that plate onto the soil, how much amount of settlement is happening in that particular plate we'll try to measure. So for that applied pressure, how much corresponding settlement is happening in the plate we'll try to understand. So from that load versus settlement curve what we plot from your plate load test, you can go on to calculate what is called as this modulus of subgrade reaction. So let's say this curve what I look at here is nothing but it's a graph what you are plotting between your pressure what is transferred through your plate onto the soil versus delta here indicates the settlement what is happening in your soil due to that pressure what you are trying to transfer through your plate onto the soil. So from this load versus settlement curve, I can go on to calculate for whatever amount of settlement that you wanted to have in that plate, how much corresponding pressure was transferred through that plate. So pressure and that amount of settlement, if I know, then I can go on to calculate. So corresponding pressure is how much, and what was the settlement that was caused in that plate due to that applied pressure. So I'll try to substitute to get what is your modulus of subgrade reaction value of that particular soil. Okay, so modulus of subgrade reaction, once you know, I'll be representing it as, let's say, modulus of subgrade reaction value, which you have got it from your plate load test. Now, whatever the modulus of subgrade reaction value for that particular soil which you have got from the plate load test, can it be considered as the same as that of the modulus of subgrade reaction value for your foundation what you are constructing there? So it's not going to be same. So what all factors depending on which the modulus of subgrade reaction that I am going to be talking about depends on. Okay, so modulus of subgrade reaction what we are going to be talking about is generally said to be a function of size of the footing, shape of the footing, depth of the footing, and it also depends on the relative rigidity or the flexibility value of the footing, and obvious that it also depends on your properties of the soil. Okay, so in general it depends on the properties of the soil, but however not just only depending on the properties of the soil, your subgrade modulus what you are trying to talk about, or modulus of subgrade reaction what you are trying to talk about, do depends on the size, shape, depth, and the rigidity aspect of that particular footing what you are looking at. So all these parameters would govern how much is going to be the subgrade modulus value of that particular foundation what you are going to be looking at. Okay. So let us try to understand some of those empirical relations, are in fact the relations what are available in the literature for finding out what will be the modulus of subgrade reaction, taking into consideration of the effect of size, effect of shape, or depth of the footing, and the relative rigidity of the footing. We have got different relations that are available in the literature. Just to quickly understand, let's say I am considering what is the effect of size, because the plate what you are using in the plate load test is of some standard size, but your foundation what you wanted to construct in the field may not be of the same size of the plate what you have used in the test. Okay, so the effect of size should also be taken into consideration in calculating what shall be the modulus of subgrade reaction value with respect to your footing. So modulus of subgrade reaction value in the case of the footing is nothing but modulus of subgrade reaction value what you have got from the plate load test into width of the footing plus width of the plate divided by 2 times the width of the footing whole square. This expression is what we are going to be making use of in the case of sandy soil deposit, and we have got another expression like KSP into width of the footing by width of the plate, where this expression is used in the case of your clayey soil deposit. And next, knowing what is the effect of shape. Let's say, for example, in the case of plate load test, I have used a square cross-sectional shaped plate there, but I am not interested in knowing the modulus of subgrade reaction value with respect to the square shaped cross-sectional plate, but for rectangular shaped cross-sectional plate, I wanted to know that modulus of subgrade reaction value. So in such particular case, modulus of subgrade reaction, what I am going to be calculating for that rectangular shaped foundation or rectangular shaped plate, in fact, is nothing but modulus of subgrade reaction value which you have got considering what is called as your square shaped one or maybe circular shaped one plus into 1 plus 0.5 into B by L, this total divided by 1.5, where B indicates the width of that rectangular cross-sectional plate and L indicates the length of the rectangular cross-sectional plate. And next, understanding the effect of depth. So considering the effect of depth, how your modulus of subgrade reaction values are to be recalculated. So let's say, for example, your plate load test is conducted at a depth of 1 meter below the ground surface. So based on that plate load test result, I have calculated what is the modulus of subgrade reaction value for your real foundation, which is supposed to be constructed at a depth of 1 meter. But however, I am not interested in later stages. I am not interested in knowing only the modulus of subgrade reaction value of the soil, which is at depth of 1 meter, rather at a depth of some other, maybe 2 meters or 3 meters, something else. So if I want to know how the modulus of subgrade reaction value is going to be, so I can make use of this particular expression, like modulus of subgrade reaction value for a foundation embedded at some depth df2, which is nothing but equal to modulus of subgrade reaction value, which I have got for some foundation which is embedded at a depth df1 into C, where C here what we are indicating is nothing but it's a coefficient which we are going to be representing based on theory of elasticity. So based on the theory of elasticity value, okay, based on the concept of theory of elasticity, we'll try to understand what is the elastic characteristics of that particular soil, based on which that particular coefficient of the soil will be determined, and based on that C value, we'll be trying to calculate what will be the modulus of subgrade reaction value of the soil, which is at some other different depths, based on the value of the modulus of subgrade reaction which you have calculated for some other depth. This is the effect of depth. And similarly, the effect of stiffness of your foundation. That's what we call it as your relative rigidity or flexibility of your footing. Okay, the effect of stiffness or the rigidity of the footing. So where we have got some expression which is given by Vesic. Okay. So before we start talking about that expression which is given by Vesic, let me say this is my foundation whose length is L. The Young's modulus value of the footing is EF. Moment of inertia of that particular footing about its neutral axis is IF. Okay. So here beam, we call it as beam, where beam is nothing but it's a long footing. That is what we call it as otherwise normalized as your beam. It's a long continuous footing. That is what it is called as, which is resting on, let's say, some soil. Okay. So though I am calling it as beam, which is nothing but it's otherwise called as your long continuous footing, is what is modeled as beam. And your original plate, okay, might have some width, might have some thickness, T. This is the width of the plate, and T indicates thickness of the plate. And now let's quickly look at the expression what is given by Vesic, where the expression for calculating the modulus of subgrade reaction value depending on the rigidity of that particular long continuous footing what you are looking at. So where that expression is given as 0.65 into ES into b to the power of 4 divided by EF into IF whole to the power of 1 by 12 into ES into B into 1 minus mu S whole square. This is the expression what we have, and here what does each term refers to? ES indicates it's the modulus of elasticity of soil EF indicates modulus of elasticity of footing material. IF indicates moment of inertia of footing. Okay, it's a moment of inertia of the footing about neutral axis. Okay, I'm sorry, there is a small correction to what I have indicated here. So here, yeah, it's not actually the plate what I am indicating. So here it is indicating you what is called as your width of your footing, and it is the thickness of that particular footing. In this direction, if I am just representing my footing like this, so this dimension is nothing but we call it as the width of the footing, and this dimension of the footing is what we are calling it as the thickness of that particular footing. Okay. And B indicates width of the footing which is resting on the soil, and yeah, so this IF value about the neutral axis is nothing but we write it as BD cube by 12, where B indicates the width of the footing, D indicates the depth of that particular beam cross section. If you can recall from your mechanics of materials course again, where we have talked about bending stresses in the beams, there we have discussed about it. So here depth is nothing but the thickness of that particular continuous footing. So which I can write it as BT cube by 12. So here in the expression, T stands for thickness or the depth of the cross section of the footing. It is not the depth of the footing, it is the thickness of that particular cross section of the footing is what we are indicating here. And any other terms? Yeah, μs indicates Poisson's ratio of soil. So based on those respective parameters, we'll be able to understand the effect of the relative rigidity of that particular footing. Okay. So modulus of subgrade reaction, what you are trying to get from your plate load test, so is not going to be adopted for all different sizes of the footing, or for all different shapes, or for all different depths at which the foundation is embedded, or for not for all rigidity aspects of your foundation. Some foundations might be relatively flexible, some foundations might be more rigid or partially rigid. So depending on the rigidity of that particular footing also, your modulus of subgrade reaction value, what you are calculating for the footing, would be depending on. Okay, so with this we'll stop our discussion for today, and in our next class we'll be focusing on solving some couple of problems which are related to the concepts of your settlements in soils, okay, which we have already talked about the theory aspect of it, but we'll be focusing on a couple of problems in our next class. Just to conclude, what is that we have all talked about in today's lecture is we have talked about briefly the different types of shallow foundation, and then we went on to understand how do we proportionate the dimensions of your combined footing, and then we have talked about in the case of your raft foundation, how do we calculate the stress or the pressure, what is getting developed at different points at different places of your raft foundation, how the stress distribution is happening from the raft onto the soil is what we have understood. And then we talked about what is meant by modulus of subgrade reaction, and what are the different factors on which this modulus of subgrade reaction would depend on. Thank you.